We discuss in this lesson power balance on a loaded transmission line. In a communication link, power is very important, so it's also important not to waste it. And wasting can be due either to power dissipation due to real materials, therefore dissipation in materials that are not ideal, but also to mismatch, therefore loads that are not matched to the source. And we want to compute all the quantities related to the power transfer between a source and the load in this lesson. Of course, this lesson, in this computation, we also include the presence of transmission lines. So we have a transmission line, and we know its parameters, characteristic impedance, propagation constant. Let's say that this propagation constant is complex, whereas characteristic impedance is real. So we are discussing the case of low losses line, in which there is an attenuation, and we cannot neglect it because the line length can be very long, and therefore you cannot neglect attenuation, but we can neglect the complex component, complex part of characteristic impedance. So we have, as you see, the expression for the voltage and the current that we already found in previous lessons. Now let's connect a load and let's see what happens when we have a lossy line and therefore we have propagation with attenuation. The variation of the reflection coefficient, unlike the lossless case, corresponds also to a variation as a function of the distance from the line in the amplitude. As you see, the reflection coefficient in magnitude at the beginning of the line is different from the reflection coefficient at the end of the line. And the difference is due to this term that represents losses in the line. So that if we had to follow the variation of the reflection coefficient as a function of d, we would observe, in addition to the change in the phase, also a change in the magnitude, so that this curve corresponds to a spiral that tends to the center of this complex plane. And this is the effect of losses that are present in the line. Now let's connect a source. So let's first have a look at this circuit in which there is a source. This is the open circuit voltage with an internal impedance Zg that is connected to a load Z0. Z0, for instance, in this case, is the input impedance of this circuit in which there is a load ZL and a transmission line of length L. So that's of length D, sorry. So Z0 is the impedance seen at this input. We can write Z0 as a sum of the real part plus J imaginary part, or its inverse as the sum of the real part plus an imaginary part. We call the two G0 and B0. So that, as you see, the voltage that drops on this load Z0 is the voltage, open circuit voltage, multiplied times Z0 and divided by the sum of these two impedances. The current instead on Z0 is simply V0 divided by Z0, so that the power absorbed by Z0 can be written from the voltage and current by this expression as 1/2 R0, the real part of impedance, times the square magnitude of the current flowing, or 1/2 G0. Notice that G0 is the real part of the inverse, so it's not the inverse of the real part. G0 times the square magnitude of the voltage applied to this load. Okay, if, of course, alpha is 0, so if the attenuation is 0 on the line, we have that the power absorbed at this cross-section by everything that is here at the right coincides with the power absorbed by ZL. So that you can also write that this term also represents the power absorbed by the load, because there is no dissipation. If instead there were an attenuation, there were dissipation on the line, in this case, of course, some of the power is absorbed by the line and some of the power is absorbed by the load. Now, there is a so-called matched condition that is represented by this expression, Z0 equal, Z0 is here, equal Zg complex conjugate, that corresponds to maximum power absorption for a given source with an internal impedance Zg by a load, which means that in order to extract the maximum amount of power from a source with an internal impedance, you must connect a load which is the complex conjugate of the internal impedance. This maximum power, that therefore only depends on the internal impedance and the open circuit voltage, takes this expression by computing the resulting quantities, and you cannot extract more power from this source more than this expression. So what our aim is to be able to represent this condition effectively. So we should always connect somehow a load matched to the source. This power is sometimes called available power, which is actually the maximum power we can absorb from that load. In general, if this is not so, then we can introduce a reflection coefficient at the source, gamma g, which is quite weird expression because unlike the common expression of the reflection coefficient, as you see, is ZL, for this case, or Z naught, minus ZG complex conjugate divided by ZL, or Z naught, if we want to compute what happens here, plus ZG not complex conjugate. This expression of the reflection coefficient allows us to write the general formula for the power absorption by everything that is on the right. In this case, we are writing PL, therefore the power absorbed by P by ZL, as the maximum power we can absorb by this source times the quantity 1 minus the square of the magnitude of gamma g. So that this general formula accounts for mismatch, impedance mismatch between the load and the source. In the general case, what happens? Okay, we can compute. We have several reflection coefficients along the line. We have a reflection coefficient that can be computed with respect to ZC and when the ZL is connected. This reflection coefficient has the common expression. We have a reflection coefficient always computed with respect to ZC that is obtained at the beginning of the line, and we call this gamma naught, that correspond to Z naught, the impedance that we see at the beginning of the line. Therefore, the expression for this reflection coefficient is Z naught minus ZC divided by Z naught plus ZC, whereas the reflection coefficient at the end, where the load is placed, ZL minus ZC divided by ZL plus ZC. And then we have a third reflection coefficient, but with a modified expression and computed with respect to the complex source impedance. The expression is this one. So that we also know how to transform from gamma L to gamma naught. This is the transformation expression. And therefore, the transformation expression also refers to a change in the magnitude of the reflection coefficient. So the relationship between the impedance and the reflection coefficient are recalled here for both ZL, gamma L, and Z naught, gamma naught. So what happens when you excite this circuit in which there is a load, there is a transmission line with losses maybe, and there is a source with an internal impedance Zg? We have a total power that is absorbed at this cross-section. This total power is the difference between the power associated to the traveling wave in the positive Z direction minus the power reflected associated to the negative wave traveling in the minus Z direction. The difference between these two is the total power absorbed by everything that is on the right here. This expression is known because we already derived an expression for this. It is this one in which we use the reflection coefficient with that modified expression with respect to the source, but it can also be written in terms of gamma naught because the reflected power, the power associated to the reflected wave, can be written in terms of the square magnitude of gamma naught. So this is another expression that holds that represents the difference between these two. As you see, from this and from this only depends on the source, this depends on the load that is here, and this depends on the load that is here, but has a different expression. We can obtain P naught plus through the power associated to the traveling wave in the positive Z direction. So this represents the power absorbed by the line and the load, so that this expression or this expression represents the sum of the power absorbed by the line and the power absorbed by the load. What is the power absorbed by the line? We take the total power, we compute the P naught plus, which is the power at z equals 0 associated to the progressive wave. We attenuate this power until we reach the load, as you see, and we multiply, which means we subtract the reflected power, which is the term 1 minus square magnitude of gamma L. And this is the power absorbed by the load. So that in order to compute this, we had, as you see, to compute the power associated to the progressive wave. The difference between the two, the total power absorbed at z equals 0 minus the power absorbed by the load, is the power absorbed in the line. When there are losses, this power is non-zero. If the line is lossless, this power is 0. And the final expression is shown here.